before this, today's training will be really hands-on session, getting more into details of Zenoh, some concept, and also some example of the code and some live demo. So the idea of this training is really a step-by-step introduction to different Zenoh concepts. So I'll go really little by little. We'll see how different things could be combined together in Zenoh. And in such a way, you can really have a plug and play kind of system when working with Zenoh. So the first thing that you need to deal with when working with Zenoh as an application developer are the APIs. So in Zenoh, we provide different APIs, either native or bindings on top of a native implementation. So in Zenoh, we've got two native libraries, one written in Rust that in the main bulk, full-fledged implementation of Zenoh, and one written in C for microcontrollers provided by Zenoh Pico. On top of those library, we also have bindings, for example, the Python bindings or the C bindings that use the Rust native library, and other APIs are under development, like C#, Java, and Go. For today's session, we're going to focus on the Python APIs, simply for the sake of time and simplicity. But the same things that you can do with Python, you can do with Rust, you can do it with C, as we quickly will see it. Right? So you got the API, how to get it, with what concerns the Python API, pretty simple. You just use pip. If you ever used Python before, is the package manager for Python. Just pip install Eclipse Zenoh or Eclipse Zenoh nightly, that the version that we're going to use today. And with that, you just got your Zenoh APIs installed on your machine. You can use Zenoh. Why are we using the nightly instead of the Eclipse Zenoh, the stable one? Because in this version, we introduce a new API, more ergonomics, a nicer user experience, and this is going to be released soon in the next couple of weeks. So better doing the training for the API to come, the next 10 days, I'll say, instead of presenting you the old API and go through the old examples. These slides will be shared with you after this meeting. So you'll see that I will go quickly through some slides, but you can use them as a reference later on. And if you don't want to use, for example, pip, here we've got the instruction how to build it from source, and just follow it, and that's it, nothing more than that. Also here on the slides, some link for your reference once you get the slides to how to access the more information on the API, on the documentation, and on their example. Similar thing for the C API, how to clone it, how to compile it, how to install it. Also for Zenoh Pico, same thing. And here more information about the C API, documentation, and example, right? Rust API, similar thing, what you need to include as a dependency, whether you want to work in a stable or nightly version with Zenoh, link to the docs, and example. So just went quickly right now, but you'll get the slides so you can go through it and just follow the commands to install it. Let's get now to the meat, really. Let's try to taste the meat of Zenoh. So what are the main concepts, abstraction, primitives, and communication models relative to Zenoh? So we've got our APIs installed in our system, but what are the concepts behind those API? The first thing that we need to think about when dealing with Zenoh are its abstractions. If you remember from the session from yesterday, I was saying that Zenoh's data-centric is adopting a named data networking paradigm. That means that we need to deal with data that has a name instead of the addresses where you can find the data. The first very important abstraction for Zenoh is the resource. What is a resource? It simply is a named data. In other terms, it's a key value, right? You get your data that has a name that we call it in Zenoh a key, and to that key you've got a value that's associated to it. For example, we can say that our key is /home/kitchen/sensor/temperature. That identifies data that is related to the temperature sensor that is my kitchen, my home. And we might have a value associated to it. For example, the actual temperature in our kitchen, that could be 21.5 degrees Celsius. The same things could be that we could have a humidity sensor, and that could be just a reading of 0.67. So here, this is the basic really concept that you need to deal with Zenoh also for the API. We've got a resource that is made by a key and a value. A key, you can see that is really an exact description of those keys. But what if we want to address multiple keys at once? So that we want to identify a set of keys. For that, we have the key expression that allows you to use wildcards in your key in such a way you can express the possibility to match and address multiple keys at once. For example, let's take the first example. That is home kitchen sensor/star. That means that in that case, the star will match everything that will come after the slash. So in Zenoh, we've got a special structure for the keys that we got different chunks that could be chained together that are separated by a slash. Like for example, if you ever use Linux like an file system, right? Slash the name, slash the children, etc., etc. So in Zenoh, a single star will match everything that can stay within a chunk. If you wanna match across multiple chunks, we also another special color is a double star. That means that it match everything in the middle, doesn't matter how long it is, with how many chunks it covers. So in case of home/star/temperature, we will meet everything that will be kitchen sensor temperature, could be home, bedroom sensor, bathroom sensor, etc., etc. Okay. We could also have home, floor, kitchen sensor, etc. You can really think about anything in the middle to be matched by the double star. In addition to that, we've got a selector. That is an expression that identifies a set of resources and allows to do some kind of selection or filtering on top of it. For example, you can have, you see that a question mark here with some selector that is say, look, got the air. In the case of the CO2 level is greater than 12, just give me back the humidity. So it allows you to do some kind of filtering on your data. Then to continue with the abstraction, you've seen the first 3 abstraction. We're going to see the latest 3. So we're going to have just a total of 6 basic abstraction that when combined really can provide the full capabilities of Zenoh. The first abstraction that we're going to see in these slides is the publisher. A publisher is someone that produces data, values, right? If you want to take a water analogy, you can think about a publisher as a spring of values. That is someone that produces some space, pays data that is published into the Zenoh system. And that is done for a given key expression or for a set of keys, for example, if you have got wildcards. A subscriber is a sink of values for a given key expression, right? Where this key expression is an exact key or a key with a wildcard. It means that whenever data is published, okay, the data will receive all the matching subscriber. And then we've got a queryable. A queryable is a well of values for a given key expression. That means that you have water there. It's up to you to go and fetch it when you want it and get it back. So when a publisher publishes data, the subscriber receives those data as soon as they're published. With a queryable, you have someone that defines as a queryable. It's up to you to go to it and get data when it is when you want data, right? So this is, if you want to remember yesterday, we've got the push model that is the pub sub, and we've got the pull model that you go to the queryable. And then we've got the communication models for Zenoh. This is the same slide that I showed you yesterday, but just worth repeating because we're going to use some of those concepts later. Remember that in Zenoh, we want to support multiple scenarios, whether it's a peer-to-peer communication, broker communication, or router communication. So in these cases, you need to understand that your application logic can be either in a peer, in a client, but your application logic doesn't change, as you can see later, depending whether you're operating on a peer mode or a client mode. So the reason why you operate in a client mode or in a peer mode really depends on the type of network and system you're operating on, and also on the type of devices. For example, if you're a tiny microcontroller, you might want to operate in a client mode. If you're like a little robot, you more probably want to operate on in a peer mode. Okay. And then before delving into the code, so some example, one of the last concepts that I would like to introduce here regarding Zenoh is about the capability of performing multicast scouting. So in Zenoh, we have the capability to discover who is around, for example, routers or peers, and you can decide who you're looking for, and to use the capability of the multicast network underneath. For example, if you're running in a LAN, Ethernet-like, local area network-like network, to discover who is around, right? In such a way, you can discover who is around, what are their addresses, and in such a way, you can then establish a session. So think about this like when you turn on your PC, you connect to the Wi-Fi, and then you want to have IP connectivity, right? You want to reach the internet. What you do is you send out a DHCP request, say, where is there my gateway, IP gateway? What are the addresses? Please send me back all the configuration. It's kind of the same thing, right? You boot up, you look who is around you, you discover, you establish a session, and then as you do, for example, in IP with your home gateway, that through your router you can access the whole internet. Once you discover your entry point or your router, you can access the whole Zenoh system. That's exactly the same analogy. Okay, so let's continue now then with the first example, really hands-on. As I said, the way that I'm carrying on this kind of training is really step-by-step building up, right? So this is really adding pieces together one by one. And by doing this, let's start from the peer-to-peer communication, just simply because we're adding pieces, right? We can see later that we start with peer-to-peer or broker. Doesn't make much difference, but please let's bear with me for the moment that we're gonna really look into the peer-to-peer communication. We need to introduce the concept one by one to be not overwhelmed with so many definitions that it could be hard to follow. So first of all, what is peer-to-peer? Peer-to-peer is a communication model in Zenoh where Zenoh peers talk directly with each other without intervention of any Zenoh infrastructure. Okay, it's quite self-explanatory. We got a bunch of devices that can directly connect and talk with each other without the need of any Zenoh infrastructure in the middle, like a router. In that case, we've got two modes of operation for the peer-to-peer. The click, that is the one that we're going to see today, and this is definitely the most common case for peer-to-peer, where every peer connects and can talk directly with each other. And then we've got also the mesh, just for you to know that peers, in this case, are partially connected to each other, but peers collaborate in the communication. That means that you might have peers that help others to communicate and forward data. So this supports more advanced peer-to-peer cases when you've got kind of a partial connectivity in the system, like, for example, a fleet of vehicles that could go in a tunnel. So you could use your column vehicles to get information out of it because you don't have connectivity inside the tunnel, for example. But again, for building up the basic concept, we'll see the click one. Let's start with the peer-to-peer communication to perform pub/sub. So the very first step. So pub/sub, what for? Why do we need to use pub/sub and how we can use it? Pub/sub is used to distribute values that are published in a given key expression to all the subscriber matching that specific key expression. You can see here, let's take our example of a thermometer, our tiny sensor that reads the temperature in my room, and then publish, for example, every 5 minutes the actual reading, right? In the Zenoh system, you might have multiple subscribers that are subscribed, for example, either to the exact key, home sensor temperature, or home sensor star, or home// temperature that will receive the data because are matching subscribers. You can see that this exactly the same key expression, this star can be expanded to temp, and this star could be expanded to sensor because it's in the middle, could be expanded to every match in the middle. But for example, home alarm status, so data will not be received by that subscriber. One very important point: publisher don't know how many subscribers are in the system and where they are. Publisher just publish data because they have the interest of publishing data. But in order to be scalable, to have a large system and an open system, is unfeasible to every time to know all the subscribers in any location, just for the sake of publishing data. For example, if I'm just a tiny sensor, I just wanted to publish data. I'm not interested if I'm just a microcontroller to know that data will be processed by some data analytics, by the mobile application, by some other system that is in the cloud or this is local to me, etc. I just want to publish data. And that is the Zenoh duty, then to deliver the data to the right place. This really allows to keep the footprint of your device, of your application really small and to be scalable. So let's assume, let's start with the first example of a publisher and subscriber written in Python. In this case, we've got, as you can see here, two peers, one publisher that publish data on /demo/example/Zenoh Python pub, and we've got a subscriber that is subscribed to /demo/example ***. In this figure, we've got that the gray line is the actual Zenoh session established between the two peers. Remember that a startup time, there is a multicast scouting phase where peers can discover each other if you operate in a LAN network, and they can establish a session, right? That's exactly what happens in this case, that the gray line indicates the Zenoh session that is established between the two peers. And with the red arrow, you've got the direction of data flowing. On this case, we've got a publisher. Clearly, data flows from the publisher down to the subscriber. And this is an example of how we can write a publisher and subscriber in Python. The only thing that you need to do, for example, you need to import your library that you installed before with a pip command. You can configure your application to work in a peer mode. Just a clarification in this case. In this example, I'm explicitly configured in a peer mode, but the default mode in Zenoh is peer, right? So this line could be skipped, but for you to show that you can have mode that could be in peer for your application, and that's how it can be done. And then you open a Zenoh session passing the configuration. Okay, when we do Zenoh.open, what happens is exactly what I explained before. We've got the multicast scouting, the Zenoh peers discover each other, they establish automatically a session, and then from that moment onwards, you are good to go. And then you can start publishing your data on a given key expression, that in this case, again, /demo/example Zenoh Python pub, and with an associated value that is just hello in this case. And then every second, we are going to publish the data via session.put, key expression file. Nothing more than that. In the subscriber, it's quite similar things. You see at the beginning, import Zenoh, create a configuration, you open a Zenoh session. Then since we are a subscriber, we are supposed to receive data when someone is publishing. So we define a callback to be called by Zenoh whenever data matching my subscription is produced. So I define my callback that whenever I receive data, I simply print out a screen. I define my key expression, /demo/example/**, so everything being published there. And I subscribe to it. So session.subscribe key expression callback. And that's it. Nothing more than that. So let's see an example for that. So, here on my machine, I can start a subscriber. In this case, I'm just available, create a subscriber on /demo/example ***. And then I can create a publisher. This guy start up, the publisher and subscriber discover each other. This guy is, in addition to the example that I showed before, slightly modified the ones that are running, but exactly the same logic where I'm printing out the number of iterations, right? But we've got a publication from Python, the session.put, and then here we've got data that is received. You can see, look, I received a put, so someone published it on demo example Zenoh Python pub, and I received the data that in this case, for example, was 28, and the data has an encoding associated to it, right? And so this is with an octet stream, so it can be decoded as UTF-8 in this case. Now, you've got one publisher on the right and one subscriber on the left. The same thing, so you can do it, for example, is to start a second publisher. These guys will discover each other, and you can see that now what happens that the subscriber is receiving two kind of publication for both the publisher. Similar to that, I can start a second subscriber. As I did before, so they all discover each other, and you can see that now also the second subscriber start receiving data. Okay, you were quicker than me. So if the path for writing out data from a publisher changes, is there a way to automatically subscribe to it without updating a subscriber script? Remember, publisher don't know where subscribers are, and subscribers don't know where publishers are. So it comes down to the actual defining of your information model when building the system, when to define the path, right? So the reason to change a path usually is because you are doing something, you are structuring your system. So it's not only the fact that you can rechange the path, that you can notify. Remember that everything is decoupled, right? So publisher don't know where are the subscribers, subscriber don't know where are the publisher, right? And it's when you define your system that you should say what is your path. Think about how when you define your REST API, right? You define a path and you know that you're going to find that information, that path. And if you change the path, well, you should update the documentation and the spec of the system you're working on, right? If you want to have some kind of dynamic path management for that, for dynamic subscription, dynamic publication, I mean, you could still have one predetermined path that you can use to notify the others what is going to be the next path that you're going to use, the next key expression. Okay. So thank you very much. Then I suggest that we continue. So I'm going to keep the slide not in presentation mode like this. I hope it's fine with you because I'm juggling a bit between different screens. So next step, we've seen pub/sub. So pub/sub, push mechanism. Then let's see an example how we can use the pull mechanism, the queryable, to implement a distributed computed value. So I presented before one of our abstraction. We got three abstractions right in the second slide. That was the pub, the publisher, the subscriber, and the queryable. Let's see how we can use the queryable now to implement an abstraction for distributed computed values. You can think of it like it was a remote procedure call kind of a behavior, right? So you want to get some data that is produced freshly on demand when you request for it. In the previous example for the pub/sub, we're saying, okay, we've got our thermometer that is publishing data every 5 minutes, but you cannot get the actual reading unless the thermometer decides to do it. That is pub/sub. With a queryable, you can implement an eval abstraction that allows you to do a distributed computed values. They say, you've got my tiny sensor that expose a queryable that allows to get the actual reading of the temperature. So let's assume I got my domotic app on my mobile phone, and I want to have the actual reading of data right now. What I can do, for example, I can issue a distributed query, for example, on /home star temperature, to know what is the temperature of my house right now. And we might have different sensors in different rooms implementing the eval abstraction. So to produce fresh data, for example, one is /home kitchen temperature, /home bedroom temperature, /home bathroom temperature. And this query will be delivered by Zenoh to the matching queryables in such a way they can produce the actual read in that moment. Okay, so it can reply back that temperature now is 25 in the kitchen, is 21 in the bedroom, 27 in the bathroom. Again, this data is not delivered, for example, to non-matching queryables and key express, for example, home alarm status. Again, in Zenoh, we are pretty much decoupled. So also in this case, when you issue a query, you simply issue a query in Zenoh without knowing how many queryables are there and where they are. The same things as I explained before for the PubSub. In order to achieve scalability and flexibility and extensibility, really in a plug-and-play function, we decoupled the different pieces in Zenoh. So as an application, we just issue a query, and then it's the duty of Zenoh to deliver the query to the right places that can potentially answer your query. So if we take example again in the peer-to-peer case, where we've got again this our Zenoh session, here we've got a get. So we issue a query on demo example ***. That query is delivered to our second application implementing the eval, that demo example Zenoh Python eval, and will reply back with that. You see that we've got the one way is you go up, it's a query, and then the reply is back. So we can implement really this pool and the request reply mechanism in Zenoh by the usage of queries and queryable. This is an example in Python again. For doing the get, you import your Zenoh library. In this case, again, configuring the peer mode, just to be explicit. You open the session. You get and collect the replies for every matching demo example ***. You receive back a set of replies, and you just print it, in this case, a print screen. Nothing more than that. For the eval, so the one that declares a queryable that can really produce fresh data, you imported Zenoh plus additional things like config, sample, and eval. You create, again, your configuration, you open a Zenoh session, and since a queryable is nothing more than someone that waits for queries and to reply back, you define on which key expression you want to answer. In this case, demo example Zenoh Python eval. And of course, you can define your callback, that whenever you receive a query, you can reply back with the data that you want to send back. And it's enough then to declare a queryable by session.queryable, passing the key expression, the type of eval, and the callback. Let's see an example now. Let's stop in the PubSub. I just started the eval that is waiting on Zenoh Python eval that will reply back with some string whenever it is queried. On the right, I'm going to do the get. So you can see what happened is that the guy discovered each other, they connected. This guy issued a query. Zenoh knows that matching queryables is provided by this guy. The query has been received, and it is replied back saying eval from Python in this case. I'm going to do it again. The same things happen, right? So you go, issue a query, and reply back. This is for distributed computed values, right? So you issue a query that you can see later it might be more distributed, and that's how to do it, really simply with a few lines of code from the get and the eval. Okay, so let's continue with the next step. Let's try to, so yesterday I presented you that we are able to do distributed storages. What does that mean? It means, and what is distributed storages and what for? So a storage is in Zenoh just a way to store data as soon as it is published and allowed to retrieve it on demand. If you read carefully this sentence and you look a bit beyond that, you can see that a storage is nothing more than just a combination of a subscriber and a queryable. So that means that a storage, from a point of view of Zenoh primitives and abstraction, is just a combined subscriber and queryable. Subscriber, as we've seen before, receives data as soon as they're published, and a queryable can produce data as soon as it is queried. In this case, it could reply back what is in memory. For example, we've got our thermometer that publishes every 5 minutes the data, and we might have a storage in the middle that subscribes to it. And again, it can provide a via queryable type of storage that can reply back the latest reading, for example. So you can get, for example, with mobile app, I can read the latest value through an external storage that can answer to it. And then this is the type of traffic that will happen when operating a peer-to-peer in case of a publisher, a storage, and a get. So you got a publisher that published data as before on Zenoh Python pub. Since a storage is declaring a subscriber, that means that every data published by the publisher will go to the storage. That is nothing more than, again, a combination of a subscriber and a queryable. The same thing will happen with a get. So when we do a get on /demo/example ***, what will happen that my query will receive the storage, because again, the storage is nothing more than a combination of storage, subscriber, and a queryable. So that data will flow in that way. And let's see an example of a storage. Well, basically, you took the subscriber example, we took the queryable example and put them together. So you configure the Zenoh with the config, not peer. You open the session. You define the key expression for the subscriber that whenever you receive data on a given subscription, what we'll do is to store the data in a hash map. So in this case, we just implemented like a hash map that will store data in memory. And then again, for the queryable, you can provide a query handler that can reply back data that were stored in our hash map in memory. Let's see an example for that. Right. So I'm going to run it here and put that storage. Here I'm going to again publish the data. You see that now the data is sitting the storage, because again it's defined as subscriber. And at this point I can do a get to retrieve data. Now what happened here, that I still had the eval running, a storage running, that you see that I queried on them example ***, but who can reply back and provide an answer for that? We had an eval in the storage. So we got a reply back from the storage and then a reply back from eval. You can see that here you can start appreciating the fact of distributed query, right? So I issue a query, Zenoh identifies what all the matching queryables in the system, depending on the configured parameters of your query, and then you can get back the results from all the matching queryables for that. Okay, so let's continue then. We have seen the peer-to-peer mode. Let's now move to the brokered mode, the brokered type of communication. So what is brokered? Again, brokered is a communication model where communication between Zenoh peers and clients is supported by a Zenoh router. And the Zenoh router actually comprises the Zenoh infrastructure. So you can really see that all the communication will go through the router. And when we add a router in our system, if you had some peer work in a peer-to-peer mode, what will happen is that the local communication stays peer-to-peer, you can see later, while a remote communication can go through a Zenoh router. When we operate fully in a client mode, all the communication will go via the Zenoh router in this way. Okay. What we need to change to move from a peer-to-peer to brokered mode? Well, you don't need to touch your application logic. It's just enough to set the Zenoh mode for your application from peer to client or vice versa. So I can see later that now in this example, we put in the code, but that can also be done by command line and configuration. So actually, you don't need to change anything else if you can configure it via command line parameter or via configuration file. Let's start talking about a Zenoh router. So we need a Zenoh router now to be able to operate on a brokered mode. What is a Zenoh router, first of all? A Zenoh router is a software process that we call it the Zenoh-D that is capable to route the Zenoh protocol between clients and peer in any given topology, whether they're a client, whether they're a click, in a mesh for peer-to-peer, and a fully connected graph, partially connected graph, etc., etc. A Zenoh router can achieve that because supports and implements a link state routing protocol for topology discovery and routing, and an hybrid logic clock that can really be useful and is used for distributed queries and storages. And we're going to have a demo to see how this timestamping of data can be used, for example, to perform some replay function in a digital twin kind of application. And then a Zenoh router can support plugins for integration with other technologies. And you're going to see a demo later on for how these plugins can be used to add a REST API, so web-based API, as well as how to integrate with a DDS. Here you got some way to install the Zenoh router, either from Docker, from Eclipse repository, or from some APT mirror, or directly from source. And once you install it, you can just run it with a Zenoh-D. You can get all the parameters with a minus help. And if you want to have some information on the bug log, it's just enough to set those kind of environment variable. Here you got the default network ports used by the Zenoh-D. So by default, it's using the TCP 7447 to set connection, and UDP port for 7447 for scouting protocol, and TCP port 8000 for the REST API plugin. You can see later. And also, your some parameters if you want to run your Zenoh router in Docker. Again, let's see some example. Pops up in a brokered mode. That's what will happen if you are fully operating on a client mode. So that's what will happen, that we got the same pops up as we did in peer-to-peer, but instead of doing peer-to-peer, we are brokered. So all the communication will go through a router. That will be the new flow of data in Zenoh. As I said before, you don't need to change your application logic of your publisher subscriber. And if you configure your application, it's enough to change from peer to client here, and everything else will stay the same. We see later that this is not necessary because we can use a configuration file that can ease this change without really not touching at all your application. Let's get back here to our terminals, and let's restart from a pub/sub that are working in a peer-to-peer mode. Right? What happens right now if I start a Zenoh-D is that those peers and router will discover each other and establish a connection. Okay? You can see that the router is not needed for local communication for peer-to-peer. I can tear it down, start it again every time I want. But what if I've got a subscriber that is in a client mode? So in this case, I'm just passing by a command line for this example, where we connect to the router that is local to us. As soon as I connected, you see that the publisher also discovered the router. So now it's also pushing data to the router, and the router delivers data to the subscriber in a client mode. You can see that if we stop the router, the subscriber will not receive data any longer, as expected. If we restart the router, you can see that they will restart the connection and things will keep flowing to the subscriber. Okay. Similar thing if we've got the publisher that instead of being in peer mode but having a client, now we got that all the communication will go through the router, and if I kill the router, no one will receive data. Okay, this is really to show you that the fact that you've got a client or peer mode, when you can go through a command line or a configuration file configuration, is something that is really related to deployment time, but doesn't change the application logic or what you are supposed to do with that. So you really decouple, abstract that the logic, what your application needs to do, what to do from how it is deployed. Okay. So let's continue. Similar things applies for the distributed computed values example. No need to change, just change the operation mode. Everything will work as before. Let's go now to the last way for communicating, that's routed communication, that we will see then how we can use it for robotics. What is routed? Routed is a communication model where multiple Zenoh routers cooperate with each other to support the communication between peers and client. So it's really a thing related to the Zenoh infrastructure. It doesn't involve at all the application, really. So that means that if you want to pass from the brokered mode to the routed mode, so just adding one step, no changes at all to the application are required. You can still configure it to your application in a peer or client mode, depending how you want to make it work. In order to have a routed communication, it's enough to interconnect the routers between them via proper configuration. And you can add them as many as you want and in any required topology. For example, let's assume that we've got two routers that are connected in this way. But a client router is connected to the second router, and a client is connected to the second router. A publisher that is attached to the first router, and a subscriber that is attached to the first router. In order to do that, to configure the connection, either can be done by a command line like this. For example, you can decide where to listen and where to connect to, or you can do it via a configuration file as before. It's enough to say what are your locators, your endpoints that you want to use to accept connection from others, and define, for example, the connection point so that where you want to connect to. And these configuration files, as I said before, can also be used by the application itself. You can see then is simply a way to get the path to the configuration file, and then you've got the mode that either could be client or peers. You can really get a deployment time. I want to deploy it in client, I want to deploy it in peer. You just need to provide the right configuration file. Nothing more than that. Let's see now an example of routed communication. So what you see here is a virtual machine on the cloud that can be reachable from outside. And I just started a router there. Now, what I can do is to start the router that I had before and to connect it to the router that is on the cloud. Now, what's happening? I've got a router on my machine that is connected to a router in the cloud. That means that, for example, I might have a pub sub, again, peer-to-peer that is local. It works as before, but then I might have also a subscriber that in a client mode that is connected, for example, on the cloud. In this case, we've got this guy that is sending data to this router. This router is sending data to our router in the cloud that will send back to our subscriber here in a client mode. You see that by just adding and configuring the routers in any given topology, you can start getting out of your device, across the internet, across the cloud, while keeping local communication local, and the remote communication can go over the internet only when needed. So to cover about Zenoh best practices, so we've seen the basic example to really get started. Well, just quite a few very important optimization that can be done by Zenoh, either under the hood or especially mentioned in the application to optimize, for example, the wire overhead that you send really on your network. One of those things is resource declaration. Resource declaration is a way to map very long strings that identifies our keys into small integer that go on the wire. It's simply a way to say, look, from now on, I always talk about /home kitchen temperature, but for the sake of brevity, I will just refer to it as number 3. So that means that you can send the long string on the network only once, agree on the hop by hop basis on what is the mapping from the long string to the integer that can save you bandwidth. And from that moment on, really low overhead from Zenoh. So when you're operating in a routed infrastructure, that kind of operation is done automatically already out of the box by Zenoh that automatically optimizes the bandwidth. If you are operating in a client mode and your time is sensor, you can say, look, you can declare it in such a way that you can force really that declaration to be sure that that's going to happen in every case. A second optimization best practice that can be done in Zenoh is to declare when you want to publish something. This is particularly useful when you've got a sensor that are operating over constrained networks or over networks that you pay your bill per bytes. So if you're just a tiny client, for example, you want to publish something, you are connected to a router, and if you don't declare your publication, most probably what happened is that your publication goes on the network. It arrives to the first router that has a vision of the rest of the system, and it drops your message. So basically, you wasted resources for nothing. But if you declare resources, it's a way to say, look, I'm interested in publishing this data. I'm interested to know where are the subscribers, how many are they, and etc. etc. Just want to know if there is someone that's interested in what I'm going to say, I'm going to publish. So you declare your publication, the router say, yes, there is someone, no, there is no one, so please don't send it on the network, it will be dropped anyway. And this is an example that a publisher subscriber example. How easy is to add those kind of optimization? Just you do a declare expression with a key expression where you want to use, and you declare a publication on that one. Similar thing for subscriber, just 2 lines of code more to get great benefits from a bandwidth and network users perspective. Nothing more than that. Okay, so let's continue then with one plugin, and Julian later on will explain more in details about plugins that can be used. One of those is a REST API plugin that can really basically is a way to expand the functionality of Zenoh. You see in the beginning that I told you, look, you got the Rust API, the C API, the Python bindings. Now I say, look, you also got a plugin that allows you to map the REST API, the HTTP methods, put, get, delete, for example, on top of our Zenoh primitives. So in such a way that you can also operate over the web the web really. So just to show you an example, we still have our 2 routers here interconnected, and what I'm going to do is to create, for example, a storage. So I'm running again my example of a storage that is receiving data as soon as it's published by the publisher. Now I can go to my web browser. This is the DNS name of my virtual machine. That's in the cloud, so publicly accessible. If you want to also test it, I'm going to pass it on the chat. The link is enough that you go to it. You can see that you are getting the latest data through the REST API from your browser that is going through the cloud, that then is going to connected to my local machine. I've got my storage on my local machine. So this also really to show you the capability of going decentralized location transparency. It's enough then to interconnect as you want your router in such a way you can really get the data from wherever they are. In this case, I really just connected my machine through a router, bridge it over the internet, and here you go. You can even access it through the browser. And this API is very useful also when we want to deal with the administration space of our Xenoh infrastructure. In order to do that, we reserve a special space that is /star/**, where we can store internally all the state that we have. You can use that space, that key expression, to access all the state of your Xenoh infrastructure. And that gives information about the routers, how they're connected, what kind of plugins they've loaded, their configuration, etc., etc., etc. So I can do that. I prefer do that right now. You can see here that this is where my plugins are stored on my virtual machine, the version, how the routers are interconnected, and etc., etc., etc. And this is really a powerful tool that allows you then to be able to administrate your system, to visualize, and to also to operate on that. And in order to showcase that, I'm going to ask my colleague Olivier Carr to really take the floor in this case, to really showcase our administration tool and the way that this REST API combined by the query mechanism can really get you a nice feeling of what's happening, how you can operate on Xenoh, and how you can potentially drive your Xenoh system through that admin space. Okay, so I think that Olivier, you're good to go, please.
Yeah, so in this demo, I will both show the administration tool of Xenoh and demonstrate the dynamicity of Xenoh, its adaptiveness to topology changes and moving things, and its resilience to failures. So if you see my terminal, I have here on my laptop some Xenoh routers running, and they are configured to be interconnected with each other in a given way, in a given topology. So what I can do is to run the tool and ask it to connect to one of the running routers. So here is a list of routers running on my laptop, which I can also display in a graph view. Okay. So for each of these routers, I can display some information about the router, typically its locators, its active sessions, its running plugins, and so on. I have a tab to load some backends, create some storage, etc. And I can also display some statistics about this particular router. So the number of bytes it's globally sends and receives typically, and I can also display some statistics for each individual link in the system. I can also ask the tool to show me in the graphical view some statistics about the links in the system. So here I'm showing all the transferred bytes per second for each link. And so here I can see that there is some traffic for session control, and basically the traffic necessary to display this tool. But if I ask it to only show me the user data, I see there is nothing happening yet in the system. So what I will do next is to run some Zenoh applications. So first, I will run a Zenoh application that will, which is connected to one of the routers. Here it is. And this application is basically capturing some frames from the camera of my laptop and publishing those frames to Zenoh. But as currently there is no subscriber in the system, nothing is sent on the network. But if I then run a second Zenoh application, which is subscribing to those video frames and displaying them on the screen. So here I am. Hello, everyone. And you can see that the flow of Zenoh messages containing video frames from the publishing application through multiple routers to the subscribing application. Okay. And now I will show you the dynamicity of Zenoh. So we could imagine that those applications, they could be some robots running around in a factory, and those routers would be deployed around the factory, maybe in several hotspots, Wi-Fi hotspots, for example. Or we could imagine that those routers are deployed in a city, in several neighborhoods, and those application would be deployed in some cars running around the city. And in any of those situations, when the application are moving around in the city or in the factory, what you would like to is that those applications they remain connected to the nearest Zenoh router, so that it keeps the lowest latency with the several things around it is communicating with. So the way you can detect that you are moving is really depends the wireless protocol you are using, if you're using Wi-Fi or 3G or Bluetooth or 6LoWPAN. So it's really dependent. But once you detected this, you can instruct Zenoh to move. And for this demo, I will just manually instruct those applications to move from router to router. So for example, I can instruct the display application to connect to another router. And you can see that Zenoh choose a new optimal path to route from this app to this app. And you saw in the video that this happened very smoothly, and the video almost had no cuts. Okay, so I can continue moving. I can also move the capturing application and so on. Okay, and each time Zenoh will adapt to the new topology. Maybe I will move to capture one step further. Okay. Next, I will show you what happens if I kill one of those routers. For example, I will kill this one, which is 11. So if I kill one of the Zenoh routers, Zenoh will detect this topology change and will find another route to route data and adapt to this failure. And again, this happened very smoothly, and we almost see no cuts in the video. I can also even kill the router on which the application is connected to, and Zenoh will again adapt and connect and find a new path to route the data. And of course, if those routers are repaired and rerun by some administrator, the new topology is again discovered and Zenoh adapts. So basically, that's it for This
Please, Julian, the floor is yours.
Thanks, Luca. So now I will get into more detail of the plugins and backends mechanism of Zenoh. So as Luca mentioned, the Zenoh router is really a software process which we developed using the Rust programming language. And the plugins on the backends are really some dynamic libraries that can be loaded at startup, just configuring the Zenoh router to configure the loading of those plugins. So a plugin is really just a shared library developed in Rust and allow usually to integrate Zenoh with different technologies. So the way we program a plugin is really straightforward. You have a Rust trait, which is similar to a programming interface that needs to be implemented. And this interface just provide a startup function that is bootstrapping the plugin. And from there, you will get a shared Zenoh session with the router that you can use to program every Zenoh usage you want for your plugin. So I will show the different plugins that we have in the next few slides. The backend, on the other end, it's also a shared library, but it's dedicated to implementation of storages in using certain database technologies. So the interface to implement in Rust is slightly different. As Luca mentioned, the way to implement a storage is really just to declare a Zenoh subscriber and a Zenoh queryable. So the trait to be implemented by the backend implementation is really to implement those two callbacks, the one for the subscriber and the one for the queryable. And then on reception of publication, the subscriber will store the data in some databases, and on reception of queries by the queryable callback, it will reply to the queries with data stored in the database. So for the plugins, the available plugins we have so far, the first one being the REST plugins that Olivier and Luca demonstrated earlier. Another one is the DDS plugin. That's a plugin that we use to bridge the DDS traffic into a Zenoh traffic, and then I will have another demonstration more focused on this DDS plugin. The storage plugin is the specific plugin which is dedicated to backend and storage management. So that will be the plugin that will also load the backend libraries and instantiate the different storages using the databases underneath. And the last one is the web server plugin. So it's slightly different to the REST plugin in the sense that the REST plugin always returns key values in the form of a JSON data structure, while the web server, because the REST plugin can also possibly send back as replies several key values for a single query. If you use star, you will get different keys and different values associated, which are represented in a single JSON object. While the web server is really dedicated to get only the content of a key, giving really the raw value back to your HTTP web browser. So the web server, in a sense, you can use it to deploy something similar to an Apache web server, but in a decentralized way and backed on a Zenoh infrastructure. So for instance, you can declare file system storage that will expose some file on your file system to the Zenoh infrastructure. And then through the web server plugin, you will be able to browse all your static website stored in your files. And you have a distributed infrastructure with Zenoh, you can imagine to have the files stored in different places around the network, and also the web servers deployed around different routers for load balancing purpose. The storages. So the storages, again, are managed by the storage plugin. And we implemented already different backend technologies in the form of various dynamic libraries. The first one, which is actually not a dynamic library because it's built in inside the storage plugin, is an in-memory backend. So that's just really a hash map in memory to store every publication that matches the storage key expression, and then to be able to reply back those publications in the query from the hash map. Another one is Rocksdb. So Rocksdb is a persistent key value store, storing data on a file in a specific file structure. And we use it so for last value persistence, meaning that by default, only the last value for each key is persisted in the database, and on query, the storage will reply only with the latest value that is stored in the database. InfluxDB, on the other hand, is a time series database, so it allows to store successive publication for each key, successive value of publication for each keys. And so in the same way for the query, you can retrieve one or several value per key, depending your query syntax. The last one is the file system. So for the file system storage, each key corresponds to one file on the system. So you can either expose your already existing file on your file system in a Zenoh in the Zenoh data space, where each file which corresponds to a key. You can also publish data in Zenoh that will, on each value you publish, will be stored inside a single file in the file system storage. So let's have a quick focus on the way to configure the plugins and the storages. So this is an example of configuration file for the Zenoh router in JSON 5 syntax. So for instance, on the left side, we have a configuration of a router that will load the storages plugin. So inside the plugin section, there is a section for the storages, which means the storages plugin. And for this storages plugin, we declare several backends, possibly several backends. Here we have only one, which is memory. And in this memory storage, in this memory backend, we decide to have storages. And here we have only one storage, which we named demo. And for this storage, we configure it to subscribe on a key expression, which will be /demo/example/star. So it means that all publications made on keys that will match this key expression will be received by this storage, and this storage will store those in a hash map in memory. The strip prefix is used actually to save some space in the database, so in this case in memory, because this prefix will be stripped from the key when storing the data in the key and the data in memory. It means that if you publish a key on /demo/example/something, actually in the hash map, you will have an entry only for something. But still, when the querier queries something on /demo/example/star, the key will be prefixed again by this prefix, and the user will correctly get /demo/example/something. So this prefix is really just to save some space in the database storage. For file system, here is another example of configuration of a router for file system storage. So we still have our storages plugin, and for the backend, we select this time the FS file system storage backend. And for the storages, we create a storage on demo with the same key expression, similar prefix. And here we have an extra configuration for file system, which is the directory where all the values will be stored in each files. Of course, you can mix all of this together, right? You can perfectly declare a single Zenoh router starting both memory and backend on file system backends, and with different storages using each one of the other. So just to be clear on the deployment on what's happening, is that, for instance, here we have two routers declaring two storages, one in memory and one in file system. on the same key expression. So each time you have a publication on a path here that is matching the storages and that is also matching a subscriber, the data will go to the first router, will be stored by the first storage, which is matching this key expression. It will go also to this one, which declares a subscriber that matches the publication, and it will go also to the subscriber that subscribe to this key expression. Later on, another client can, for instance, perform a get, so a query on /demo/example/*, and this query will go to the first router that will fetch the data, matching data from the storage, but also be forwarded to the second queryable here, which is the second storage, to fetch the data and reply back the data to the client. So at this stage, as you can see, both storages have the same key expression path, so they are both storing the same key values. Still, we have a mechanism in the Zenoh API that by default, when you perform a get on a key expression and you have several matching queryable, if ever your application will receive twice the same key, only the latest publication, so the one with a greater timestamp, will receive the data and will present to the user API only one value per data. So this behavior is named in Zenoh the consolidation, the query consolidation, and there are several modes of query consolidation that can be used to also be able to receive the full set of values for a single key, for instance, if there are several storages matching the key. Okay. So I will not go in deep detail to all the querying mechanisms. We can go in this in further presentation, but you have the slide in any case. But as we go in short in time, I will switch to another presentation more focused about the Dds plugin that we implemented for Zenoh. So the Dds plugin is implemented in Rust, and we actually bundle it in two ways. The first one is really a plugin, so a dynamic library that can be used to be loaded by a Zenoh router in the same way that it loads the storages plugin, the REST plugin, or whatever plugin we may have in the future for MQTT, Kafka, or whatever technology we can imagine to bridge with Zenoh. So in this sense, the plugin bundle is useful to have a single deployment in a single process of a full bunch of plugins, storages combination. On the other end, we also deploy the exact same code in a standalone process that we named Zenoh Bridge DDS. So it's really just a main operation that is statically linked with the DDS plugin, but also with the REST plugin that is activable on option. And this allows really to have a bridge from Zenoh to DDS to behave like a Zenoh application or a Zenoh peer. So the bridge can be deployed in client mode or in peer mode in the same way than Zenoh application. So for instance, it may allow you to deploy, to avoid the usage of this router and to have a direct communication between two bridges in the DDS domain. But you can also deploy it in a client mode to be connected only to one router, or in a peer mode to connect also to the router plus directly peer-to-peer with another bridge or with other peers application. So how does this Zenoh bridge works? First mode is a default mode, which behaves this way. So you have a DDS bridge in a DDS domain. This bridge discovers, for instance, some data writer on a DDS topic named topic A. And in response, this DDS bridge will create a matching data reader on topic A associated with a Zenoh publication on a Zenoh key named /topic A. If you have a remote bridge, this remote bridge will be discovered by Zenoh communication or by Zenoh scouting or directly by configuration. And this other bridge may be connected to another DDS domain where it discovers some data reader on topic A. In response, this bridge will create a data writer on topic A associated to a subscription on the Zenoh key /topic A. And at this stage, the Zenoh bridge with Zenoh protocol will declare this subscription, which will be received by this publication, and the data will be able to flow from the data writer to the data reader, and from the data reader to Zenoh, to this Zenoh subscriber, to the data writer, and then in the other domain up to the data reader. So the way we map the DDS topic in Zenoh is really just to use a slash as a prefix for the topic. But if ever your writer is also using partition QoS, we also use the partitions as a prefix to the path. And we also have an option which is in the Zenoh bridge DDS, which is named the scope, for the user to be able to choose himself a scope that will be prefixed for all the Zenoh key. So for instance, this allows to bridge different independent DDS domains, but that might use the same topic names. So they are distinct in the Zenoh global data space. So a key point of this default mode is that there is no routing of DDS discovery. So you know that DDS discovery protocol can be very consume a lot of bandwidth because it's intensive in message exchanges. So with this mode of communication, there is no DDS discovery flowing between the bridges. Only Zenoh discovery is flowing, and actually it's just a declaration of the subscriber on /topic A. Moreover, there are also other options in the Zenoh DDS bridge that allow to group a set of publications. So for instance, let's imagine that this domain, for instance, has hundreds of topics. We just have to configure the bridge to use a scope, for instance, which is named, for instance, /domain1, and to configure also the bridge to declare a grouped joint subscription on /domain1/**. On all of a sudden, for all the subscription made in the code for all the hundreds of topics on the wire, still there will be only one subscription message flowing, which will be the one on /domain1/**, because basically we are saying, hey, this Zenoh bridge just subscribe to everything under the scope /domain1/**. And that corresponds to all the hundreds of key expressions that we may have for the hundreds of DDS topics. So thanks to this mechanism, we are able to really scope the DDS discovery into a very teeny exchange of message between the two bridges. Still, this default mode is suitable for a static DDS system. Static in the sense that in advance, each application knows in advance all the topics it declares, and they don't rely on dynamic discovery of other readers or writers to create their own readers and writers. On some use case, such use case actually might happen, and this happened, for instance, in ROS system for the implementation of ROS services or ROS actions, where ROS waits to detect the creation of some data writer or reader on some topics to create its own data reader and data writer. So to cover those use cases, we introduced a second mode, which is the forward discovery mode. So to activate this mode, you need to have both of your bridges setting this configuration. And in this configuration, when the Zenoh bridge discovers a data writer, it rather publishes a Zenoh message saying, I discovered this data writer. And the remote Zenoh bridge, in response, will create its mirroring data writer in its on the bridge associated with a topic A subscription on Zenoh. Because of this, some application here will detect this data writer in this domain and might react, creating matching data reader on topic A. And in this case, this bridge will forward some information about those declaration to the remote bridge, which will create a mirroring data reader in the remote bridge associated with a publication. And there we are back in a previous scenario where the data can flow from the data writer to the data reader in the other domain. So again, it's not really a full forwarding of the complex DDS discovery protocol. It's just let's say a compact way to forward the discovery messages in the Zenoh style. And moreover, also for the specific to ROS, for ROS2 mechanisms that use an additional specific topic to send some discovery information that are specific to ROS and allow to reconstruct the ROS graph. We also forward this specific topic from ROS, but in a more optimized way between the two bridges. So it really allows to have the complete ROS graph from the remote side. Okay, so the feature, just a summary of the feature that we have with the Zenoh bridge. So first one is that we are able to group the Zenoh publication and subscription for a minimal discovery traffic that might be important over the internet or over wireless communications. You can configure a list of allowed topic to be routed or denied topic to be routed in order to keep some topics internal to your DDS domain and not have to route everything over the internet. Also, in the use case of the Indie Autonomous Challenge, we added a configuration which is per topic downsampling. So just the use case, for instance, in Indie Autonomous Challenge, they add some very intensive publication topic inside the car, let's say at 100 Hertz. And they cannot afford to send this 100 Hertz publication over the wireless network to their base station. So for this, we added a configuration allowing to specify that for this topic, we downsample to only 5 Hertz the publications that are routed by the bridge. So this saves a lot of bandwidth on the wire, and 5 Hertz is still good enough for remote teleoperation. Transient local QoS is also supported via a mechanism of caching of publications that is made by the Zenoh bridge. And the remote Zenoh bridge, if ever it has a transient local reader, will perform a query to get back the historical data from the remote bridge and provide them to the late joiner data reader. So discovery and routing information are also available through the Zenoh admin space, so the same admin space that Luca and Olivier demonstrated earlier. You can see in this admin space what are the DDS entities, reader or writer that have been discovered with their QoS, and also the route that are established by the Zenoh bridge between the DDS topic and the Zenoh keys. Plus, also you benefit all the Zenoh feature like the different transports, the routing, and the fault tolerance mechanism that Olivier demonstrated. So, time for a quick demo. What I will do on my laptop, I have a Ubuntu VM in which I have a ROS2 DDS system, and I will deploy a Turtle Sim, which is a simulation of a robot using ROS2. I will deploy a bridge, which will be connected to a Zenoh router deployed in our cloud infrastructure named demo.zenoh.io. This router also has the REST plugin. And from this REST plugin, I will be able from a single web page to publish some twist message over HTTP that will be routed as Zenoh messages to the bridge that will translate those messages as DDS publication received by the robot to move the robot. In the same way, I will also, the browser is also subscribing to Zenoh using the HTTP server sent event mechanism. It will subscribe to all the publications made by the robot on /robots, meaning the logs coming from the robot. So let's have a look to this here. So here first on in the cloud, I'm starting my Zenoh router. Here I'm starting a turtle sim on domain 1. So this is DDS domain number 1. And here I'm starting the Zenoh DDS bridge in client mode connected to demo.zenoh.io, listening on DDS on domain 1 and using this specific scope for prefix /bot1. Okay, and from here, to get back my page. So already what you can see, if you go to this web page, share this in the chat. You can see all the administration space of Zenoh, but also of the Zenoh bridge, and you can see all the participants, the writers that have been discovered in the DDS system with their QS. You can also see the routes that are established between the DDS readers and writers and the Zenoh system. So, and for this, from this web page, so we just reload the web page. Go on /bot1. So I can drive the robots using my arrow keys. And if ever the robot is hitting the wall, he is logging some information, and those logs are republished on DDS and are received here in my window. Okay, now another step. I will deploy a second bot on using another domain, DDS domain named domain 2, and I will use a bridge on bot 2. So let's do this. Here I'm starting the turtle sim on 2. I'm starting another bridge on domain 2, still connected to the one to the demo.zenoh.io. And from here, for instance, if I using bot 2, I can drive the second robot. If I'm using bot star, I can drive the two robots at the same time. Okay. So next step of the demonstration, going a little further. So now what I can do is also to add an InfluxDB storage inside the router. So I will deploy the storage plugin and configure an InfluxDB backend. And this backend will be configured to store all the publication on the scope /bot1. And later on, I can start a Zenoh application connected to this router that will perform a get on /bot1 pass to retrieve all the past publication from InfluxDB and replay the same publication, but on pass /bot2. And this publication will go to this robot that will drive the same way that the first robot. So let's do this. First, I need to start InfluxDB service. So here I'm starting it in a Docker service. And now I need to configure the backend. So just to show you, that will be, for instance, a configuration file that we can use to start the router and to create the storage startup. So there is a declaration on InfluxDB backend connected to my local host InfluxDB service, and with a host to storage here on this key expression. So matching the publication that I made from my web browser. But rather than to start this with a configuration file, what I can do also is to use the admin space of Zenoh to do some publication on the admin space of Zenoh to create those InfluxDB backend on storage. So at first, for instance, I'm doing a HTTP put using this data, which is the exact same properties and what is described here, and using the paths that correspond to my router. So on demo.zenoh.io, router, local, config, the plugins, in the storages, I create a backend in InfluxDB. So here we are. So you'll see, actually, the router just received my publication on HTTP. It loaded the storages plugin, and it also loaded the InfluxDB backend, and it's available. And now I can create my storage. So in the InfluxDB backend, I'm adding a ROS2 storage with this configuration that actually corresponds to this one. And here the storage is created. So from now on, if I'm publishing something from /bot1, I'm driving the first robot, for instance. All of this had been stored here in the InfluxDB backend. And now, from my host here, I can run this little toy that we have in our demos that is connecting to the Zenoh router. Will perform a get on /bot1 scope and will replay everything on /bot2. And here we can see all the publications that are made, that have been read, and that are replayed on the other robots. So just for you to show, here is the exact query that have been performed on Zenoh, which goes to InfluxDB. So we are querying on this key expression, but as an option, we specify that we want a start time 0, meaning that we want the full list of publications for this single pass, and we get the list of publications from InfluxDB. And that's it for share. And give the floor to the next presentation, which is Julien Loudet, that will introduce Xenoverflow.
So while we are doing the handover, I just wanted to do a remark about what you've seen with Zenoh so far. And it's really, I hope that you were able to appreciate the really capability, simplicity of Zenoh API, and the capability that you can really focus on application logic, and then depending on your system, you can really go decentralized and distributed by interconnecting deployment time, the routers. That also allowed then, we've seen with the demos from Olivier and Julien, to really get out of the device and to really have a plug and play feeling to Zenoh. So in such a way that once you already have a system there, you don't need to change the rest of the system because you just want to add some functionality. Because one very important point from the demo from Julien was that you had really the DDS system, but you were able to just plug in Zenoh, add additional functionalities in a completely decoupled manner without touching and changing the old system, that is the DDS system used by ROS, and enrich it with a new functionality provided with Zenoh while keeping all the compatibility with old system. Really is a few abstractions that are very powerful that can be combined together, and it can be really add on top one of each other depending on the needs, and compose really to get a more large scale and a complex system as you go, without go and touch every component that needs to be reconfigured or change the mode of operation of your running system. Hope that this aspect was clear. Also, like to remark it, because I think there's a very cool aspect of Zenoh that really can shape it as you go. So, Julien, please.
Yes. I was letting some space for questions, if there were any. All right. So in that case, I will move on. And so bear with me with this final demonstration. And so about Xenoverflow. And so Xenoverflow is leveraging Zenoh. So first, a few words to remind you the presentation I gave yesterday. So Xenoverflow is a framework for the cloud to think continuum. And so it allows developers to logically structure and decompose their application in units. And so the idea is that Xenoverflow will automatically manage them. And so one of the assumptions that I made yesterday is that either Zenoh and Cyclone DDS are in use, and especially Zenoh. And so to take that out of the picture, I will already configure Zenoh. So don't need to get into the details. The idea is that with this configuration, we're setting up everything we need for Xenoverflow to run. So as I will be juggling with the terminals, let me start one where I have a Zenoh here that I will start a Zenoh here, sorry. Okay, so this is done. So now that Zenoh is in the background, let's start and try to understand a bit more Xenoverflow. So to understand Xenoverflow, we have to understand a bit more about data flow programming. So data flow programming is a way to represent your computation, and that way is through a directed graph of nodes that can execute concurrently. So data flow programming is not something new. The formalism, let's say, of data flow programming was done in 1973 by Gilles Kahn with the Kahn processing networks. And it's used a lot nowadays, although no one is being very explicit about it. So we formalize it because there are interesting results, especially determinism, if your data flow is correctly declared and configured. So what it allows us to do as well is to focus simply on the application logic. So with the data flow, we specify which are the operators, the sources, the sinks, how they are connected, and that's it. You don't need to do any pipe, any plumbing, really focusing on the application logic. So as you might have guessed, with Xenoverflow, you're going to do, and we are going to do together, some data flows. So the objective of my small presentation and hands-on is to create the following data flow. And the idea is we'll have a node, a source called name source that will read from a file, and it will read names. From these names will be sent to another node, the compute greetings, that will simply prepend hello to the name that was fetched in the file, send the result, so hello name, to the print greetings that will write the result in an out file. So right now, for the purpose of that demonstration, we're using files, so in and out. But in real usages, in real cases, we could have a database instead of files. So we could read from the first database here in compute, do all the logic, and maybe write it out on another database. Okay, so how do we get there? So Xenoverflow is a 3-steps process. So first, you have to implement the nodes you need. So the source, the operator, the sink. Then you have to describe the data flow graph. So you have to describe how the nodes are connected. And lastly, you need to deploy. All right, so let's get started. Let's implement some nodes. So when I say nodes, you need to understand that we have 3 types of node. We have sources. And so the idea is really for a source to fetch data from the outside world and to bring it into the data flow. The operator receives data that is already in the data flow and we perform computations. We see an operator as a node that will not do any IO. It will simply compute. Ideally, an operator is stateless, but as I will say in the next slides, we allow nodes and operators to have a state in Xenoverflow. The final type of node we have are the sinks. So the sink, the idea is to take the data that is the end result of a computation and to take it out back into the world. So for instance, in a database. So nodes in Xenoverflow must implement their own interface. So there is an interface with source, there's another interface for the operator, and another interface for the sinks. The main differences between these nodes are the number of inputs and outputs, as well as how they're triggered. So going back to the Hello Xenoverflow, we see the source really has one output that is sent to the compute routine, which is an operator which has one input and one output. That output is sent to the sink, and the sink has only one input. All right. So I mentioned also that there's a different way to trigger the nodes in Xenoverflow, and that's especially true for the operators. The operators have what we call input rules. So input rules are a special way to decide when an operator should execute. So why we've added input rules in Xenoverflow to operator is to allow more complex operations, such as synchronization. So for instance, let's assume you have a time constraints on the input. For instance, you need the threshold between the timestamp of A, B, and C to be lower than a certain amount. So in order to do that, you need to be able to express this before you trigger the computation. So if the timestamps are not good, are not aligned, you can decide in the input rules to trigger or not the computation, to drop the values and wait for others. Okay, so we have sources, sinks that have one input and output. We have the operator that can have multiple outputs and inputs and can be triggered with input rules. Okay, so what's the other thing that I mentioned earlier is the state. So all nodes in Xenoverflow can store a state. So that state is, for instance, if you need the previous computations or if you open the database connection, typically you can store that in the state. The only thing we do not provide as is in Xenoverflow is the state management capabilities, meaning that if your node fails, for instance, the state will be lost. All right, so in the end, when you have developed your node, what you have is we allow you to do dynamic loading between codes. So the idea is that depending on the language, you will either compile it and have a shared library, such as Rust and C++, or you would have a script for Python. So this end result, this shared library of this script will be dynamically loaded by Xenoverflow, as in we'll know where we can locate it and we'll bring it to the device where it needs to be run. So looking at some code, as this is a bit the purpose of today. So here I created, let me move the Zoom interface a bit to the side for me. So we have created the ZF Hello World, and we have different files. So we have the source here. So the source implements, as I mentioned, the interface. So this is the class source. And so we have the initialize and finalize. So here we handle the state, as I mentioned. And then we have the run. The run which is triggered, which is where you would put the logic of your source. So for instance, where you would read from the file and then take the name and encode it for the next operator. We have the sink and we have the operator. Let's do the operator. So similarly, we have a state with initialize and finalize, and there we have the input rule, as I mentioned. So in our particular case, the input rules are extremely simple. Whenever we receive a data, we say true, meaning, okay, you can perform the computation. So that computation in here is to getting the name that we received from the previous operator, decoding it, and prepending hello to the name. So lastly, we have the sink. So let me increase the font a bit. So similarly to the source and the operator, we have the class sink that we need to implement with the state management. So where we initialize and finalize. And finally, how we interact with the greetings and where we write it. So here we are decoding it and then writing it to the file. Pretty straightforward, pretty easy. Okay, so coming back to my presentation, I said that we had scripts that will be dynamically loaded. So here are the scripts. Now, how do we connect them together? Because as you can see, I never declared where I would connect them. So to connect the different nodes of your application, you need to describe the data flow. So describing the data flow in Xenoverflow, describing the data flow. So in Xenoverflow, describing the data flow is performed in the YAML file. So this file is a contract, as I mentioned yesterday, that really will be enforced by Xenoverflow. So taking the different nodes that I mentioned earlier, we see that in this file, we are declaring the source name, we're declaring the operator, compute greetings, and the sync print. We're also declaring the links, so how they're connected. So I've hidden some information such that we can take some time to focus a bit more. So for instance, let's start with the operator. So the operator, the first thing you have to mention is the URI, which is where we can find the script. So for now, we support the file schema. And so that tells us exactly where we can find the node on the device we want to run it. Later on, we want to extend that schema to support, for instance, a registry or URL that will tell us where to find, like on some other device, the file we need to run, and so to import it directly from there. This registry will obviously leverage Zenoh and the storages to link a bit with the presentation done by my colleagues. Then we need to specify the inputs and outputs of the operator. So this name, the ID name and the ID greetings, if I go back quickly to the code and to the operator, we see that this name is the one that we have in the code. So this is how the connections are made. So the input and output you specify in the YAML file are the ones that you need to specify in the code as well. All right. So this is it for the operator. Now let's go to the source. So it's very similar. The source has a URI to tell us where the file is located and the name of the output. So for source, as there is only one input, one output, sorry, you don't need to specify the name in the code, as given there is only one, it has to be written in this. So Xenoverflow does this for you. Similarly, syncs, they only have one input, and you must specify the URI, so nothing new here. Lastly, the links. So the links, you need to specify and be very explicit about which output is connected to which input. So here we have the source, and so the output name here is connected to the input name of the compute greetings. Similarly, the compute greetings output is connected to the input of the sync. So the output here, greetings, is connected to the sync input here. All right, so to finish, we can see in the folder we've created, there is a hello world YAML that gives, so for instance, here the file, it's the location on my laptop of where I can find the source script. All the rest is exactly identical to what I have in the presentation. All right, so we have the scripts. So we have our nodes, we know where to locate them, we know how they're connected with the YAML file. So now how do we deploy them? So that's extremely easy. So we need to start a Xenoverflow daemon on where we want to load them. And this Xenoverflow daemon is know where we can deploy the correct nodes. So first off, assuming we want to deploy them on different Xenoverflow daemons, we have to specify a bit of mapping that indicates, okay, so in order to run that node, I need some specific tags, I need some specific configuration. So I will add in the YAML file these mappings. So now, as we added these mappings, do we need to communicate to each daemon in order to deploy the entire data flow? So the answer is no, because thanks to Zenoh, the Xenoverflow daemons that are running on the different device are aware of each other. And so they can, once one receives a YAML and knows that it involves other daemons, it will transfer the YAML file such that each daemon deploy and runs the nodes that it needs to deploy and run. Okay, so enough talk. Let's see a bit more action. So as I mentioned, as I showed at the very beginning of the presentation, I started at Zenoh. So now let me start a Zenoh daemon. So to give a slight, to give just a little bit more. So we have a runtime YAML here. So this is to specify how we load extensions. So these extensions are, for instance, the Python interpreter. So we need to give a bit more information to the daemon as to where Python can be located. This is just that. So let me start the daemon. Okay, so the daemon is now running. So that means that we have a daemon on my machine. So let me see if I can see it. So I can start ZFCTL. I need to move the zoom. Yes. So as you can see, the Xenoverflow, so we have a command line tool. And so the command line tool sees that there is a Xenoverflow daemon running on my machine. And here, by listing the instances, it's telling me, okay, which flows are actually running. And we can see that no flows are running right now on my machine. So let me change that and start a daemon. So I need to wrong shortcut. Why is it not running? I don't know. So I need to start. Obviously, this is the demo effect. Previous command. Okay. I know what I did. Okay, now it should be running. Perfect. So let me start. So here I am telling the Xenoverflow daemon through the command line again to launch the hello world flow that we defined earlier. So as you can see, the Xenoverflow daemon started instantiating the flow that we described. And so for that, let us check if an instance is running. And indeed, the layout is not ideal. We see that there is a flow that is running right now on my machine. So that flow, if we recall the data flow graph, reads from the file that is here, hello world in. And so we see it's empty. So now if we add information, so for instance, echo sales teams to that file, we'll see that the Xenoverflow will be triggered. And yes, unless I specify, yes. So what tail-f does is that it reads the final lines of the hello world.out. So what happened here is that we wrote on hello world in sales teams. It has been read by the source. The information was sent to the compute greetings operator that wrote hello sales team to its output that was read by the sync and that wrote it to the hello world ZF out file. So to show that it's really running, I will say hello Xenoverflow, and we'll see that it will be written in the out file. Awesome. So here is Xenoverflow. So it's a very, very short example and introduction to how Xenoverflow runs. Now, so the try is what I showed you. So I didn't have the time, nor I think you, it was too much information for a first introduction. But so there are some noteworthy features that we have in Xenoverflow. So for instance, we have deadline missed notification that are both local and end-to-end. So what we mean by that is we can set a time for an operator, for instance, to do a computation. And if that time to perform the computation is missed, let's say, so if the time is 100 milliseconds and it took 150 milliseconds to compute, then we will inform the user through a specific output rule that the deadline was missed. We have the same functionality end-to-end, meaning we can set a timer for a subpart of the graph or the entire graph to compute. And if the deadline is missed, the last node in the end-to-end deadline will be informed. We also have periodic sources. So for instance, you can set a period for your source to be triggered, so the run. So maybe reading the file every 2 seconds. We support loops. So loops in the entire definition of the graph, which is quite convenient for robotic types of application. Logging and replay. So recording everything that's happening at the source, and so that we are able to replay it later on. And as you've seen earlier, a command line interface. And with this, I conclude my presentation about Xenoverflow.